Okay. Well, it is with great pleasure and also sadness that I get to introduce Leonardo Krapp, perhaps for the last time as somebody with a University of Arizona affiliation, because although he has been a postdoc here for a while, and especially recently a 51 Pegasi B fellow, he is now leaving us for cooler and less dry pastures, heading to the University of Concepcion, where he'll be a member of the faculty. And today he's going to talk about some of the really incredible work he's done on understanding circumplanetary disks. Leo is an expert not only in planet formation, planet disk interaction, but also multifluid instabilities and high performance computing, including technical algorithm development and GPU acceleration, amongst other things. So take it away.
All right, thank you. Thank you for coming to the last talk of the semester, especially in Tucson when it's so hot and you want to escape from the heat and go somewhere else. Thank you, Caitlin. And I also should say that I should apologize because this talk was scheduled for February, I think, but because essentially the paper that we were going to talk about was not out, but by then I asked Serena if we could reschedule. So thank you for doing that. Now we have published the results. The paper is under review. It's still under review, but it's out on arXiv. And this talk is a short summary of that research project that I will say that it was essentially a long project that we started maybe a few years ago, but it took us a while to get it out, to get everything out, because we needed some numerical developments before we could tackle the question that we wanted. And that numerical development was, I think, also slowing down this project a little bit. And this has been possible thanks to a number of collaborators, but I just want to emphasize and highlight the great collaboration with Caitlin Krapp, who has been driving this project for a few years and being so patient with me during this research. So thank you. And yes, as she was saying, I'm going to start my faculty job in a few months. I'm moving to the city of Concepcion, University of Concepcion in Chile, and many people that I talk to, they ask me, where is that? Because everybody's familiar with Santiago and everything that is up there, north from that, like San Pedro de Atacama or Alma, for example, the BLT, Paranal, biggest telescope, all the telescopes are here, this is Atacama. So I'm gonna be south. This is not dry, you can see it's very green and foresty. So looking forward to that. And everybody's going to be welcome there, I guess. So hopefully we will have some Fargo 3D meetings there and science discussions in the future. It's not that far from Patagonia. For those who like mountains and ski, everything from here to south is very beautiful. Patagonia starts somewhere here. It's line. Let's start with the geography discussion, and let's go to the actual science that we want to talk about. And I was highlighting the location of ALMA in the previous slide, because of course ALMA has been our primarily driver for all the science that we are doing. And we have all these great data from the different protoplanetary disks that we see in the submillimeter. We think we are looking here at millimeter dust grains that are at the midplane of different protoplanetary disks. And we see a lot of substructure, gaps, rings. The question is still out there. And after a decade of observations, some people in the field, I think they believe, but they're a bit disappointed about the fact that we are not seeing protoplanets or many protoplanets that can explain these observations. And of course, that is the most interesting or promising candidate because we are interested in planet formation. So we want to see those protoplanets there. This is perhaps the most interesting candidate so far, PDE-70. These are two observations of the system in different wavelengths, and there's clearly a signal. And I think with certain confidence, there is an agreement in the planet formation community that there's one or two planets confirming this system. But aside from PDE-70, we don't have confirmation from protoplanets in the other cases. So why? Of course, one of the reasons is they're not the cause of that substructure. There are many other mechanisms that can explain that. But the other reason is that we perhaps do not understand the thermodynamics and the dynamics of these envelopes to the point that we can explain extinction levels and other spectral signatures that can come from these systems. So it may be that we need to do more studies, and the planets are there, but they're invisible to our telescopes. Of course, if you're looking into these systems, we have to be very careful about how we treat gas dynamics and thermodynamics, because that's what we're looking at. And that's our work here, at least my work, I suppose, was to try to advance the models and the techniques that can help us to understand the gas dynamics in a planet disk system and the thermodynamics in these systems. And one important question here is whether these protoplanets are forming or not circumplanetary disk around themselves. And of course, this is an old question of circumplanetary disk formation. It's a matter of study for the different reasons. And I think the first motivation was trying to understand Galilean satellites or natural satellites in our solar system, for example. But now we are, of course, interested in an exoplanet. So we want to understand the formation of circumplanetary disk, not only for the reason of the planet-moon system itself, but also for the detectability of the systems. We cannot see the signal from the planet, but maybe we can see the emission from the circumplanetary disk. So which type of emission we can get. But first of all, are these systems forming circumplanetary disk? Every time we see a 1-2 Jupiter mass-like planet out there, or at least in the case of PDE-70, are we looking into a circumplanetary disk, or are we looking into something else? And to answer that question, we need to first understand how circumplanetary disk formation take place. There are many, it's a long literature. I'm not going to go through all the details. I'm just going to give you a brief summary of circumplanetary disk formation. And our work, this talk, is essentially focusing on that question. And except for a handful of works, maybe 3-4 works in the literature, the majority of the papers that you will find in the literature focus in or try to answer the question of circumplanetary disk formation from the point of view of a ballistic or cold framework, pressureless framework. So the idea is that you solve the dynamical equations of a system of planetesimal or solid bodies around a planet or a core, and with the assumption that there's either no fluid, there's no pressure, or there is pressure, but the system is cold, so pressure doesn't play any role there. And in that approximation, there has been, the motivation from this started, I think, in the studies of binaries back in the 60s by Leonardo and Paczynski, but soon after people moved to the protoplanetary disk. And the idea is that you have a cloud or a swarm of planetesimals moving around a core, and there's some sort of angular momentum dashes. So people have been thinking about this as an angular momentum conservation problem. When you have near the orbit of the planet, you have some specific angular momentum, and if you average the accretion process in a careful manner, you can get what is the angular momentum, or specific angular momentum that can be delivered to the core and be transformed into, for example, spin or rotation of the solid body. But these numbers is still unknown and requires a lot of modeling. Can be guessed by numerical simulations, for example. And people has been doing that. In the 90s, numerical simulations were possible. There were a lot of studies, especially in two-dimensional hydrodynamic simulations with no thermodynamics, just locally isothermal equation of states, where people were looking into accretion process and planet disinteraction migration, but they also were looking into the flow in the Roche law of the planet, or inside the Hill radius of Jovian planets, where they could measure the specific angular momentum and could estimate, for example, this value. And if you can estimate that value, somehow that was, for a long time, that was taken as a proxy for circumplanetary sizes, for example. In the 2011, this paper came out from Martin and Lewin, where they trying to explain the formation of a circumplanetary disk with many different approaches, with many different frameworks, from ballistic to hydrodynamic simulations with viscosity. And I think the important outcome of that project was that what sets the size of a circumplanetary disk is the torque served by the central object, what's called sometimes tidal truncation. And you can measure from the numerical simulations the tidal truncation radius, which is giving you where the basket of the significant amount of the mass is encapsulated around the planet. And this is one of the simulations from that work. And the outcome was that this tidal truncation effect give you a size that goes between 1/3 of the Hill radius to something like 0.4 of the Hill radius. And this has been confirmed and compared with different models and many different simulations. This is a summary of circumplanetary formation and a nice paper by Warren Canup, where they compare the outcome from different numerical simulations with theoretical predictions. In this case, they show what is this angular momentum bias in terms of the Hill radius, which is a proxy also for size of the circumplanetary disk, and is in this agreement with the predictions from tidal truncation simulations. The size of the circumplanetary disk will be between 0.2 and 0.4 of the Hill radius if you eventually form a circumplanetary disk. The majority of these works were done in the either ballistic or pressureless approach or isothermal, local isothermal approach, with extension of Egelif and Bate, which I think was the pioneering work that moves from that ballistic approach to now a thermodynamic or radiation hydrodynamics approach, where you now take into account an energy equation for your fluid. You have heating process and a cooling process that might be not in perfect balance. So that will determine whether you have a pressure support that is important or not. And if your pressure support becomes very important, you will not form circumplanetary disk, you will form a spherical envelope or the ellipsoidal envelope around your planet. So what sets that pressure support? Well, in this work, the approach was like trying to understand that transition as a function of different parameters like the mass of the planet and the opacity of the system, which is dominated by small grains at temperatures below 1,000 Kelvin. And the conclusion was that for a given, well, they put this the result in terms of what's called here scale height of the disk in terms of opacity divisor, which is a number that refers to different fraction of dust grains, for example, in your system. As you increase your opacity divisor, you decrease the fraction of dust grains, so you have a lower opacity. And the scale height is essentially a proxy for this height or circumplanetary disk. And as this scale height increases, you transition from a circumplanetary disk to a more spherical envelope. Few years after that, the question was again addressed, but now in different terms. And there was this series of work, but Schlage et al., where they actually framed the question in terms of the inner temperature versus planet mass. So your planet, there's some compressional heating process, there's accretion. So at the center of your heliosphere, there's a planet and it's heating the gas, and that has you can have a very hot inner region with a few thousand kelvins or even more. And whether or not you form a single planetary disk in the end was a matter of how hot was your system for a given planet mass in that inner region.
So what is the yellow, the temperature?
So you have density here. This is temperature.
Yeah.
And I think this some angular velocity
So the
normalized.
middle one is the temperature?
Yeah, so this is temperature. And you can see if you go, I think if you go from top to bottom, you get a colder inner region and you form a CPD. And also the mass in this series of plot may be changing as well. I don't see quite well in the labels, but I will try to improve that in the future presentations. But that's the idea. You have a more spherical envelope. And if you cool or you add like a temperature cap, so temperature cannot rise above 2000 Kelvin or so, you may form a rotational support gas envelope or circumplanetary disk. So this works has a few follow-ups, and more recently there was this also interesting work from Ernst et al. Where there's not really radiation hydrodynamics here, it's three-dimensional hydrodynamics, but they explore two limits, the isothermal limit and the adiabatic limit. And in the isothermal limit, you are more likely to find rotational support envelopes. In the adiabatic limit, you are likely to form a more spherical envelope. So for us, after looking at this, we came in for a while, we were thinking, well, there must be a critical cooling time, because in this case, that you can think about the isothermal case as a perfect rapid cooling case. And the adiabatic case is the one that has the slowly cooling on the infinite cooling time. So in between these two limits, there must be a number in terms of cooling time that tells you how you transition from an isothermal to an adiabatic. In the previous work, that question was addressed in terms of opacity or temperature, but we believe there's a more general criterion that you can come out, which essentially calculated this cooling time. So how close to an isothermal case your system has to be in order to form a single planetary disk? So that's the question. Again, you have two different outcomes. You either go to a spherical envelope or a single planetary disk. And the quantity that determines, or the criteria you can look for that, is essentially rotational support or specific angular momentum. And the other part of the problem is cooling time. So to answer that question, we use a Fargo 3D code that require a number of improvements in the past years, which transition from a multifluid code to now a multifluid code with non-uniform mesh capabilities and species and advection algorithms that allows global simulations, because you have to think that the CPD, these studies are, part of the critical parts of this work is to include the dynamics of the entire protoplanetary disk. So we are not really simulating a local patch around the planet, but we have a global disk around a central star, and then we have to zoom in into the protoplanetary disk. Zoom into a protoplanetary disk to a planet location to see dynamics there. So that's computationally challenging, and we develop a number of techniques that help to make this more efficient. In the end, radiation hydrodynamics is a bottleneck for other reasons, so there's some limitations that we are on the track to improve that as well. So we develop these algorithms, they are out as well, and we couple all our algorithms with this system of equations. This is the multifluid model, hydrodynamics for gas and gas, where we take into account the momentum transfer between the different gas species. And the radiation hydrodynamics, in this case, is approximated by the flux limit diffusion. This is the equations from the energy and the relative energy. We consider stellar heating, viscous heating. And this is also a strong approximation, and I have a few things to say about this. That is one step in between locally isothermal and more complex radiation equations, and more expensive too. Perhaps the novel thing is that we couple the evolution of the radiation hydrodynamics with the evolution of the dust, because the opacity is dominated by grains, dust grains. They are dynamically evolving following these equations. So the opacity changed locally. By using some approximations, we map the dynamic of the dust into the opacity, and we input that into the radiation model. So that's a novel thing that I think this has been, to the best of my knowledge, the first work to accomplish that. This is an example of one of the models. This is a global simulation. So here we see the perturbations in the velocity, in the vertical velocity of the protoplanetary. This perturbation are excited by the planet that is here. And as we zoom in, we see the opacity is not uniform in this case, because the dust grains are not well mixed with the dust, with the gas, sorry. So they trace these gradients. And also we see the mass flux. Red here means inflow and blue means outflow. This is a density contour showing the spiral waves signed by the planet. Just to highlight the setup that we are working on here, working with here. And this is a movie that we made, and this is showing the dust distribution after 20 or 30 orbits. Around the star, as you zoom in, and apparently Wi-Fi is downgrading the quality of the video significantly in the projector. And that's a volumetric energy of the CPD, so we can see the rotation of the material around the core, and the planet is essentially a potential in the center of that cloud. So we ran different models. Here I'm showing the most representative cases. We have a standard case, which is a radiation hydrodynamics with no dust dynamics. We have a multifluid case, which is radiation hydrodynamics with dust dynamics. We have an isothermal case, no radiation hydro, no dust dynamics. So in the isothermal case, this is essentially an average plot of the density with the velocity field. We see this standard picture that has been out for more than a decade or more. So there's nothing really new about this plot, it's just a comparison. Well, there's one thing that is new, I will tell you. But in terms of the velocity field and the density, we see what has been shown already for many other orders. Here, you have a circulation of material, accretion comes through polarizations, and then you have an outflow at the midplane. And in the isothermal case, where the pressure support is minimal, you form a circumplanetary disk, and you can kind of see how the aspect ratio is increasing. This is the density. But when you go to radiation hydro, it looks more spherically symmetric. It's not really a circumplanetary disk there. Why? We're going to try to see that. And there's a transition case in between these two, which is the multifluid, when it is it's not quite a circumplanetary disk, but it's moving towards that. Maybe it can be a thick disk. Again, there's not really, in terms of the meridional flow and the density field that we see here, this has been seen by many other authors, but no one has addressed yet the question of, well, why you see this in terms of rotational support versus cooling time. So that's essentially the main outcome of the main takeaway from our work. When you look into the energy equations, you can measure or can estimate a cooling time. Basically, you're looking into the internal energy, the budget of internal energy that you have in your system. And you can also assume that your transport of energy is going to be dominated by this term here, which is the flux, radiative flux, cooling through radiation. And you can calculate, or can you estimate a cooling time using these two equations. And as when used at the beginning of the simulation, after 1 or 2 orbits, this cooling time is this dashed line here. And it's normalized by the orbital time of the planet. And I think to give you a rough number for those that many are not familiar with this, when your cooling time is order unity, it's to believe that you're cooling fast. You're cooling in a time scale that is comparable to orbital time scale. So usually cooling times order unity or lower are, I think this is not correct, but they are called as isothermal cases, or locally isothermal cases. Final cooling is non-isothermal, but that's perhaps the connection that you can make at this point. And as time evolves, the cooling time increases. You can also plot the specific angular momentum for the different time scales, and you will see that initially the specific angular momentum normalized by what will be a Keplerian orbit around the planet. So ballistic approach, no pressure support, you're rotating in a Keplerian orbit. And you can see that decreases as well as a function of time. So there's a correlation, which is not crazy, it's something that you expect. As your cooling time increases, your specific angular momentum may decrease, or at least the vertical component of your specific angular momentum, which tells you the degree of rotational support on the axis of rotation. Yeah. So you can look into different orbital time scales for the system, and you will see that for the standard case, the cooling time keeps increasing, and consistently with that, the specific angular momentum keeps decreasing. So that's why in the standard case, for example, you don't see circumplanetary disk. Your specific angular momentum is so low, so it's on the order of a few percent of the Keplerian angular momentum, Keplerian specific angular momentum, so there's no really rotational support. And that correlates with the cooling time that is above unity and keeps increasing. Now you can put different models. So that was for the standard model. Now we put the multifluid models, and we also have an additional model where we decrease the opacity, we decrease the amount of dust by 50. So 50 times less dust mass, and that's what we call low here. So we decrease the opacity. So here what you see is again this cooling time normalized by the Keplerian orbital frequency, or the orbital frequency of the planet around the star. It's a function of the distance to the planet. This is radial distance. The planet will be somewhere here, and this is normalized by the Hill radius. And you can see that the cooling time decreases as a function of distance and becomes very low, where you are actually approaching the limit of locally isothermal, at the scale of the Hill radius. But as you approach the planet, your cooling time increases and goes above unity here. So you can compare these two plots and come out with a criterion that tell you, well, if you know what is your rotational support for your isothermal case is the best case scenario for rotational support. That's the solid curve here. So you can ask the question in a way, well, how short has to be the cooling time so I can recover this rotational support that I get in the isothermal case? And we were looking into what we call the truncation radius, which is the largest possible size that a circumplanetary disk can have in the. And at that location, to get a rotational support of the isothermal case, you need a cooling time that is at least an order of magnitude lower than the dynamical time scale. And I will say that based on this plot and this result, you need at least 2 orders of magnitude. If you want to get that rotational support, you need at least 2 orders of magnitude lower than your dynamical time scale. So it's quite a short time scale. And the idea of this criterion is that here we are not talking about opacity, planet mass, or temperature. We just are looking into how radiative cooling works, and we are calculating that right? The cooling time, or yes.
Oh, sorry, I think you just answered that, but I was thinking if you have if you were able to have a larger circumplanetary disk, you will end up with a more massive planet or not necessarily?
Well, the amount of mass, the size of the circumplanetary disk, just so this rate is just telling you where an effective torque is able to remove your angular momentum, so you don't have rotational support. But it does not necessarily tell you how much mass you can accumulate. So the mass depends on the mass flux that you have through the heliosphere. That's scaled with the mass of the core.
Okay.
But also will depend on how you regulate accretion through different physical processes. One of that process is cooling.
Okay.
So if you have a rapid cooling, you may accrete more faster. You may, and that's actually the next.
Okay.
I think the next or the other slide, which we don't only care about circumplanetary formation, but also the evolutionary phase of the planet. How rapid it's going to grow if you change the cooling time scale. This is just a warning that I want to raise, which is that we are using the flux limited diffusion that may not be the most accurate radiation approximation, numerical approximation for this problem. And I'm showing here something that is a proxy for optical depth. And whatever is blue here is very optically thick, and whatever is red is optically thin. So there is a transition in the envelope from optically thick to optically thin that is very clear, and especially when you decrease your opacity. And every time you have this type of transitions, so flux limited diffusion is defined to work very well in the diffusion limit or in the free stream limit. It recovers the two limits, but in between, if you have a gradient, the approximation is not necessarily accurate there. So there's room for improvement here. Although I don't think it's going to affect the criterion, but it's just going to affect whether a given planet or a given initial condition will end up having a CPD or not in the way that you're treating your energy equations. So this is another comparison between the different models. Again, in the isothermal case, this is the azimuthal velocity around the planet, and you can see that the disky structure here is very, in this case, you have the rotational support. It's very prominent. And you can see how there's an inflow. This colors indicates the inflow and outflow. Red means inflow. Blue means outflow. So material is coming through polar regions, and then some of the material is escaping through spiral waves that are excited by the planet. And it's clearly non-axisymmetric. So taking this azimuthal means is somehow misleading. But as you move to radiation hydrodynamics, you see that the topology of the flow changes. You have a bit less of rotational support. You have the same, inflow outflow, but this is a very thin disk. It's getting thicker, and here there's not really a disk. You don't see any rotational support at all. Just a cloud of a swarm of fluid particles moving around, very slowly rotating around the planet. And in general, what we see is that as you go from isothermal to radiation, your flow is not in free fall and is subsonic, basically. So that's another important point to highlight. So there are many words that simplify this problem and assume that you have a supersonic free fall material coming towards the planet. This is not the case in the radiation hydro. That's why we show here a proxy for the Mach number. So back to your question, whether you can, how this affects, for example, the time scale for the growth of the planet. And we cannot really answer that question thoroughly. But what we can do is a comparison with one-dimensional models. So our three-dimensional simulations can only integrate a few orbits on a very small time scale in the lifetime of the planet or the protoplanet. But 1D models can do that. And there's a history of 1D models that explain nicely how a planet grows in different phases, going back to Pollack, 86, and many others after. And you have to integrate your system for a few mega years. So that's virtually impossible for these simulations. But we can actually extract the 1D profiles and compare with some of the outcome of those models. So we can look into density, temperature, luminosity, and different values and variables. And what we see is that at the iterations of our simulations, our 1D average profiles resemble an isentropic envelope in all the cases that we integrated. So there is a point in which you have some rotational support here, but as you move inwards, you always get an isentropic. And with Caitlin, we have good reasons to believe that this is not a true physical outcome. This might be just due to the poorly resolved physics that links the core of the planet and the operations that we are solving here. And that is because we don't have the resolutions nor the physics that can solve the entire scales of the problem. We have to increase our resolution significantly, way more to actually go to the core. But it's not only a matter of numerical resolution. There's a lot of physics that you have to take into account, which has to be with the role of self-gravity and a more sophisticated equation of state. There are other processes that can take care of the cooling, the ionization, recombination. There are many things that have to be taken into account if you're going to go all the way to the core in these 3D models. But still, I think it's interesting the discussion on, well, if you see these isentropic envelopes, and there are 1D models that are actually consistent with that. So even if your physics is misleading and you have some artificial heating, that may be consistent with some heating that you may have by relative feedback, some other process in the inner regions that leads to an isentrope. And if you get an isentrope, what you get is a very slow contraction. So the time scale and for the planet to shrink from a few hundred Jupiter radius down to 2 Jupiter radius may be significantly larger if you have an isentrope than if you have circumplanetary, where you actually, you grow in mass until you become stable and you rapidly contract here, and you go from a few hundred Jupiter radius to 2 Jupiter radius in a very short time scale. These are two different, completely different ways in which the planet will grow. And our 3D models are suggesting that you can have this isentropic, spherical, slow, contracted growth. That is a bit speculative yet. We need to actually put more physics there to answer that question. And I think to finish, we're all, of course, interested in our first slides of, well, what can we tell about the observational part of this? What's our predicting power, if any, on what we can see with different instruments, either ALMA or now, of course, JWST. So Caitlin is making a lot of progress and helping a lot to digest all the observational part. And this is a very preliminary result that we are looking into it. But the bottom line is that when you compare the spectral energy distribution at different wavelengths for JWST, for mid-infrared, we see some excess introduced by the planet envelope with respect to the circumstellar disk. This is not a new result. This has been shown already. For example, you can look into the work of Shilagi et al. 2019. But essentially, we are putting new physics, especially in multifluid parts, so we're still digesting some of the results. And one of the conclusions that we have so far is that if you see this excess in the infrared, on the mid-infrared, you should also see something in millimeter wavelengths with ALMA. So if you're unable to see a protoplanet with ALMA, hopes that you see that in a shorter wavelengths, I think is unlikely. It may be unlikely. It's a strong conclusion, but this test indicates that it's not easy, and it's in agreement with previous works. Apparently, if you keep going to shorter wavelengths, then your circumstellar disdominates, so you're not able to penetrate and see deeper inside. Unless you carve a very deep gap, remove all the material, so you have a giant planet, few Jupiter masses in a late stage of the formation process for some of the standard parameters that we believe exist in this disk. So what to do next?
Sorry, could you explain me a little bit more on that SED? How did you measure all those spectrophotometry points? Do we need to zoom into the field of view of that planet, or just the whole aperture is just covering the whole planet system?
I guess I can give you a short answer and you can elaborate. But the idea is that we take cubes of data around the planet, and we put that into Ryan C3D, for example, and we calculate those SEDs. And then we take cubes of data away from the planet where you get only disk, circumstellar disk, and you compare the spectrum. But there's some details on the different instruments that I'm not sure if they random C takes care of that.
And there's no noise in those. This is just showing what the underlying SED would look like across those wave bands. And so they're not being convolved with different beams for, say, NIRCam and MIRI, which is one of the problems, right? If you had, you would, resolution-wise, you'd be better off with NIRCam, but wavelength-wise, you're better off with MIRI. But the contamination from the disk makes MIRI harder.
Okay, thanks.
You're like a super mega UX kind of.
Well, the problem is MAG-AOX is not in the right wavelength,
Yeah.
right? It's optical. It doesn't do you any good if it's there's no H alpha. I mean,
They do have H alpha.
no, there's none in there's no H alpha in these. I mean, not only is there no H alpha in these simulations, the simulations do not predict that you should see H alpha for this type of system.
Would you see bracket? Yeah.
No, it's just not.
It's just not hot enough.
It's just not hot enough. There's no shock. There's no shock in these simulations, basically. It's
You
very
have
weak.
to go to mid-infrared.
But I think still the point is that if you see something, if you're hoping to see something in the mid-infrared, it means that you are also seeing something in the millimeter wavelengths.
Yeah.
So if there is not really a bright source in the millimeter wavelengths, and what we can do now, because of the multifluid simulations, we can actually calculate the different extinction levels by the different particle sizes, and maybe have some predicting power on the evolutionary phase of the gases to allow you to see something.
Ilaria has a question. I actually was going to ask that question too. So how massive is the planet plus envelope? The axis at 10 microns seems quite large. If you see that, it is quite large.
Actually, probably it's not the mass, right? At this, probably temperature. But anyway, sorry. Yeah.
We're looking into Jupiter mass-like planet here. And the mass integrated with the envelope is not more than, it's less than 2 Jupiter mass like planet.
It's at 30 AU.
30 AU, our system is calibrated to 30 AU. And the results are fairly consistent with other estimations at Jupiter mass planet at 50 AU, for example. In terms of the ratio, I think between the ratio that we see in the flags in the mid-infrared. I'm not sure, was that your question, Ilaria?
Yes. I guess a short wavelength is more a combination of temperature that dominates, and the long wavelength is the mass of the envelope. I was surprised that it's so strong, the excess at all wavelengths, but anyway.
Especially around 10 micron, that area.
Yeah, we can probably dig more into it, but these are very cold. We don't get, in these models, we don't get temperatures that are about 1,000 kelvins. And probably the highest temperature in this model, I think the hottest spot was about 500 kelvins or so. So these are cold.
So that's not really the old temperature, just not temperature.
Yeah, I mean, if you keep increasing your resolution, you will eventually reach a very hot region. Things may look different in the short wavelengths. I think we will keep looking. That's the that's the future ahead, and the future also involves improving our models because there's a large scale that we do not resolve, which is about 300 really of the planets, at least for a 38U Jupiter mass-like planet. And I think the conclusion about the cooling time and the cooling criterion to get rotational support is somehow safe or agnostic to all of this. But if you want to go into observational signatures, and you also want to understand how, growing time scale for the planet, better comparison with 1D models, for example, you need to put that physics, you need to put that scale in the simulation. You need the self-consistent link between the core and the disk. And this is challenging not only for the computational cost in 3D. They're not such simulations, I believe, that can reach that scale and take into account all the important physics that happens through all that scales in a self-consistent manner. But there has been recent nice progress by Malu et al. In 2023, where they have actually 2.5D model that solves all the scale from the core out to the Hill sphere. Again, you're limited. Either you solve your protoplanetary disk and you don't go all the way down to the core. You solve your core and don't get the protoplanetary disk. It's a compromise. We're hoping to get that in between in the next years with Kipling and some other collaborators. But yeah, that's I think that's pretty much all I wanted to tell you. So thank you for your time, and I'm happy to take questions or comments if you have any.
Okay, questions? Yes, teacher.
Yeah, very nice talk. I actually have a question related to the model simulations you presented. There is the one called the standard model and the other one called the multifluid. And it seems like the multifluid has more advantage over the standard model. So why you're not just using the multifluid instead of just still advertising for the standard ones?
Yeah, so the reason is, so this project has a number of corollaries as results. One of that was a comparison between dust dynamics that trace your opacity in a different way than standard models where you test what mixed with gas. And there's a second paper that we are writing now, which goes into more details, or we are starting with the writing process that goes into more details and try to compare better to which range the well-mixed approximation is good enough, and in which cases the multifluid must be taken into account. Why the dust distribution matters? Because for small grains, they may be well mixed or may not. They would be settled, and the different degree of settling may change the optical depth and may change the way you see the systems. So we are actually working in that paper now. I think there's like a range of parameters, especially if you have like a subgrid model with significant turbulent diffusion, where the well-mixed standard approximation may be reasonably accurate.
So for now, for instance, the Jupiter mass planet at like 48U, the two models are quite similar.
I think in terms of the observational implications of the observational constraints that we are getting, they are similar. But that's a preliminary conclusion. I mean, in terms of the dynamics, they are very different.
Okay.
There's a question, Joan, would you like to unmute and ask question?
Hi, great talk. I would love to see some of those movies again. But my question is about Jupiter as a possible example of a CPD. I mean, well, the Galilean satellites kind of make us think that it had a CPD that was rotationally supported. Do you think of that as something, is that unrelated to these models, or could your models explain that?
I think what we are getting here is that eventually through the lifetime of early Jupiter phase, the cooling time was short enough that allowed for a substantial rotational support. Why the cooling time was so short, which type of process we're taking care of balance that towards short cooling, I don't know, I cannot tell you. But that's what our research tells you, essentially. There's not really an inconsistency here whether a given planet mass at a given location can form or not the circumplanetary disk. It's just a matter of how short is your cooling time. And it's very likely that in the late stages, when you dissipate the gas, your cooling time will get shorter and allows for substantial rotational support.
Okay.
Okay, thanks.
Great talk, Leo. So you showed that as you go from 1 orbit to 30 orbit, the cooling time actually increases. So consistent with that is you go from more disk-like structure to spherical.
Yeah.
Do you think there's important physics there to understand, or it's just simulation settling to an equilibrium does not have implications for long-term disk?
So what happened in this case is we get accretion that drives the compressional heating, and that since you keep accreting, material keeps falling towards the center, that keeps adding heat to a system. So to get a better understanding of that, you need a better model of your inner region, where you have like a smoother potential, how you deal with accretion there, and how you deal with radiative feedback, which will be the accretion luminosity that comes from the planet and is able to heat the gas through the accretion. So I think that has to be done. But it's gonna be more, I think understanding that is important if you want to really know whether a given system is gonna form a circumplanetary or not, like a given disk, mass, and distance from central star, like a very specific parameter set. We know the answer already.
Andrew has a question. Andrew.
Oh, yeah. Hey, Leo. Great talk. Thanks. Sorry, I couldn't be there in person. So I wanted to maybe follow up quickly on Joan's question. I thought one of the possibilities that had been discussed for moon formation, that it was maybe happening at a later phase than you're modeling here, right? And sort of more of a last gasp when everything is sort of much less dense and optically thin. And then I guess the other thing I also like Anho, I actually wanted to ask about the cooling time thing again, and actually just forget what was the main driver of that increasing. Was it the luminosity going up, or the luminosity going down, or the temperature going up?
First part of your question / comment, yes, later stages will be presumably favored towards rapid cooling. So that's maybe, that is definitely not what we are modeling here, but I think my answer to that question was that you know the cooling time that you need to get rotational support. Doesn't matter which stage are you. It only matters if you care about the planet mass and the system that you're trying to explain. And the second part, yeah, the dominant effect here is increasing in temperature due to the PdV work term in the energy equation. That's driven by the accretion of the material. Luminosity is not changing.
Okay, and I know it's, I mean, obviously the challenge is the huge computational cost, but I mean, should it be possible to reach a steady state, you know, quasi-steady state? And do you think that's very far off?
Eventually you reach quasi-steady state. So the mass, for the standard case, we are in quasi-steady state. The mass and the cooling time eventually stop increasing. But by then you form a spherical envelope.
Okay,
Andrew,
but I
you're
thought they were.
muted. Oh, yeah. And I was just telling you, Andrew, you were muted. If you have further feedback.
No, that's great. We can obviously talk more, but yeah, this is really good stuff. Thanks, Leo.
Thank you.
Any other question? I actually have a question about the envelope cases, and then how long would it last? And then when you talked about mass loss, what observationally can we expect about the mass loss rate?
We didn't really model here. In our models, we're still on the accretion phase. We are not really taking into account mass loss, but eventually you will reach, you will carry a deep gap, and your gas supply will be limited.
Yeah.
You will reach a detach phase or the late stage in the planet formation growing phase diagram. You will lose your gas. We don't have any estimation for that, guys. We are looking into early stages.
So how expensive is your calculation actually for you have it only how many orbits did you have it for total?
So it depends on the model. We have reached 100 orbits for some of the models. Depends on the resolution as well. Multifluid is a bit more expensive. It's proportional to a number of fluids. But the real bottleneck here is the radiation, the treatment of radiation, hydrodynamics. That I think there's a lot of room for improvements, because that requires a lot of communications, integration to converge. And when you have a lot of communications, then MPI, of course, that's not scaled properly. And after a few GPUs, then you are limited. So for we were using the B100s at Pleiades, 2 to 4 B100s per simulations. With multifluid, we're talking about 3 weeks. With standard, 1 week, something like that, per model.
Mm-hmm.
So you need a good summer to get.
Yeah. Okay, so last call for question.
Yeah, one last question. Could this framework also, and not just for the, will work with this for the interpretation of the ALMA geological issue, but also on the current population or distribution of planets already formed?
You're looking into exoplanet demographics.
Exactly.
Yeah, I think that's
or backwards. I mean, if they kind of form your
model. Yeah, it's always kind of the goal and motivation behind this. But to give it, I think we, Caitlin can of course give you a more detailed, perhaps, vision of this. But my interpretation is still like a fuzzy, blurry outcome. There's not really something very concrete to be said about it. But the majority of the motivation of the research is motivated by the exoplanet demographics, because we see these mini Neptunes in super Earth.
Yeah.
And why they stop accreting. So, they are in these inner orbits. Cooling must be very efficient at some point. And then they stop, so the cooling become very inefficient because they stop growing. Or there are other processes related to this. Those are kind of the question behind this, but we don't have a very concrete answer to that. I know, Caitlin, if you want to add something more to that.
Okay, thank you for your wonderful talk, and let's thank Leo again. Good luck with your new adventure.
Thank you.